up chapter 10 with 10.2.3. We're going to skip 10.2.4 and 10.2.5. So, chords and angles. What more can I learn about circles? Some more kind of cool relationships. Like I said, circles and triangles have some unique properties when they blend together. It's pretty cool. So, what if it is a semicircle? So, what is the measure of an angle when it is inscribed in a semicircle? An arc with a measure of 180 degrees. Consider this as you answer the questions. So, in the diagram at right, the measure of the minor arc, well, is 180 degrees. So I don't know if it's the minor arc necessarily because it's, the entire thing there. So I think that would be the middle of it, cuts it in half. And that would make this a 90-degree angle, right? Angle P has to be 90 degrees. Why? Because as we learned in lesson 10.2.2, the inscribed angle is half of the intercepted arc. So if the intercepted arc is 180, half of that would equal 90, and we would have ourselves a right triangle. So it says if you drew QR, what would be special about it? And again, what we're going to find is that this is the diameter, right? It cuts the circle right in half, even though it doesn't look like it. And then it says, let's go ahead and make some other things that go ahead and... So that would be a right angle. That would be a right angle. So if point P was moved to different locations on the circle, would the measure of QPR change? It wouldn't. It would still be 90 degrees because it would still have the same intercepted arc. So any of these angles, inscribed angles, would be half, and it would still be 90 degrees. So in the diagram at right, UV is the diameter. So what kind of triangle is triangle UTV? Well, it must be a right triangle because that would be 90 degrees, right? The inscribed arc is 180. I'm sorry, the intercepted arc is 180, so the inscribed angle would be half of that, or 90. So if TU equals 6 and TV equals 8, well, 6 squared plus 8 squared equals 10 squared. That's the diameter, but it's asking for the radius. The radius would be half of that, which would be 5. So the radius would be 5. Now again, what's the area of this triangle? Well, if we turn it into a rectangle, it would be 48, right? 6 times 8 would be 48. We only have half of that, so base times height divided by 2. So the area is going to be 24 units squared. 75. A polygon is inscribed in a circle with each of its vertices lies on the circle. How are the angles of the quadrilateral inscribed in a circle related? So consider this as you answer the questions below. So what do these angles have in common? Which is kind of cool. So for ABCD, inscribed in the circle at right, solve for x. Well, here's the thing. If this is 100 degrees, if this inscribed angle is 100, this intercepted arc must be 200. Well, if this intercepted arc is 200 degrees, that means there's only 160 degrees left from here to here, which means that the inscribed arc of that would be 80 degrees. So we know that that has to be 80 degrees. And again, the idea being, I'll try and clear this up and do this again real quickly. If this inscribed angle has an interceptive arc of 200, which it does, the only portion that's left would be this portion right here. You know what, I think maybe changing colors might make sense. So this part would be 200 degrees, right? Well, let's change to red. Well, then this part that's left has to equal 160 because there's 360 degrees in a circle. Well, if I divide 160 by 2, I get 80 degrees. So that's how we know that that equals 80 degrees. So as we continue along, it says, Alejandro notices something. I think that the opposite angles of a quadrilateral inscribed in a circle are always supplementary. Is she correct? Prove your conclusion. Well, I'm not going to prove it, but yeah, she is correct. The idea would be if I took this angle and this angle, I would get this angle would give me this intercepted arc, and this angle would give me this intercepted arc. So if you add the two opposite sides of a quadrilateral up, the intercepted arc equals 360, which means half of that would be 180. So yeah, that means they're supplementary. They're always supplementary. 1076. Tim asks, what if two chords intersect inside a circle? Can triangles help me learn something about these chords? Copy his diagram in which the chords AB and CD intersect at point E. Timothy decides to create two triangles. So he goes over here and he says, all right, well, let's make triangle BED and triangle CEA. So he finishes those off. It says add those to your diagram, which I just did. Compare angle B and C. Well, look, B has the same intercepted arc as C, which means I don't know what they are, but I know these angles have to be the same. And the same is true for D and A. D intercepts this arc, and A intercepts the same arc. So these angles have to be the same as well. So what does that tell me? Well, kind of hard to see right here. I'm actually going to hand draw this one. That tells me that I have similar triangles. So how are these related? They're similar. I know because of angle similarity, back from an earlier chapter, right? So we have angle similarity. That proves that. That means everything's proportional. So if DE equals 8 and AE equals 4 and EB equals 6, what does EC equal? Well, think about it. Across from one arc is 8, across from one arc is 4. So obviously this triangle is twice as big as this one. So if across from 2 is 6, well, across from 2 must be 3, because 3 doubled equals 6. So I know that EC has to equal 3 because I proved that these are similar triangles, and if they're similar triangles, they have to be proportional. All right, let's go and open up. I should have just assumed that it's not going to open. I'd be curious to know why sometimes it opens and sometimes it doesn't. Alrighty, so moving along to 1077. It says in lesson 10.2.1 you learn that a chord is a line segment that has its endpoints on a circle. So hopefully we know that this is a chord because its endpoints are on a circle. So examine the chord LM in circle P at right. If the radius is 6 units, so I know that this radius is 6 units, and if LM equals 150 degrees, that's the arc length, right? The minor arc length is 150. I know that central angle has to be 150 as well. So if I just take this triangle out of it, it looks something like this. Well, it wants to know, what is LM? Well, LM is this whole thing right here, but what I'm going to do is I'm going to cut this in half and I'm going to use some trig. So I know that this is 75 degrees. I want to know what this distance is. So opposite over hypotenuse, so the sine of 75 degrees is going to be equal to x over 6. So I'll grab my calculator, I'll turn it on, I'll make sure I'm in degree mode. I know that the sine of, if I cross multiply, right, x is going to equal whatever the sine of 75 times 6 is. So I get 5.8. So this is 5.8, but I have 2 of them. This whole LM is 2 of them. So I'll just multiply that by 2, and I get 11.6. So LM must equal 11.6. And again, guys, I'm going through this fairly quickly, but it's assumed that you know trig by now. We just reviewed it a couple of weeks ago in these videos. It's assumed that you're kind of okay with that cross multiplying, all that good stuff. So what if you know that the length of a chord, so now we're going to work a little bit backwards. So now they're telling us that we have the chord. How can you use that information to reverse the process and get the arc? So we're going to draw something with a diagram of a circle with a radius of 5, has a radius of 5, and it has chord length of 6. Well, if I cut that in half, I'm going to get a 3 4, 5 triangle. Hopefully you guys see that, right? Pythagorean theorem. I cut the 6.5, I get a 3. I recognize, oh man, I have a right triangle. It's the ever famous 3, 4, 5 triangle. Hopefully we now know that across, it's as easy as 1, 2, 3, right? So this must be a 30-degree triangle. And if this is 30, I have 2 of them. So this whole thing must equal 60 degrees. Could have used trig on this, but it was a special right triangle. So I took the shortcut and used a special right triangle. Alrighty, jumping down to 1078, A, B, and C. Some of these are a little bit more quick. Some of these are a little bit more slow, but that's fine. So use relationships and diagrams to solve for x. Justify your solutions. So in this one, we know, let's go ahead and finish this off like we did. We'll make these triangles, which might help us a little bit here. So I know that this angle has to be the same as this angle because they have the same intercepted arc. Likewise, I know that this angle has to be the same as this angle because they have the same intercepted arc. So hopefully there's no confusion about that. I know that I have angle-angle similarity. Not only that, but I have angle-angle-angle, right? These are vertical angles, so these are definitely similar triangles. So because of that, I can use proportions and ratios to figure this out. This is 2 to 3. I know that KL equals 8. Well, if KL is 8 and this is 2 of it, then KQ must be 6, right? 6 plus 2 is 8. So I have that whole distance there. And now I'm just going to go ahead and use ratios. Across from 1 is 3 and across from 1 is 2. So I have this ratio of 3 to 2 when I look at the big triangle. 2 is 6 to x. So, look, 3 times 2, so 2 times 2, it looks like x must equal 4. Again, using ratios. All right, let's go down to RT. So this one's kind of a little bit interesting. I know that I have the diameter here, right, because I have 2 radii. So this whole thing must equal 180 degrees. And hopefully you remember that. That means that this whole thing must equal 180 degrees, which means that this must be a right triangle, right? Because the inscribed angle is half of the intercepted arc. So if the intercepted arc is 180, that inscribed angle must be 90. And now I'm just going to use special right triangles to sort of finish this thing off. The ratio here is 1 to 2. So it's as easy as 1, 2, square root of 3. This must be a 30-degree angle, right? Because this is 1 and that's 90. So 1, 2, square root of 3. Well, if this is 30, this must equal 60 degrees. That's a 30, 60, 90-degree triangle. Hopefully that made sense. Again, what's tricky about this is we're bringing so many chapters together, and I know I'm going through them fairly quickly, but I don't think anybody watching this video wants me to teach chapter 10 and chapter 4 and chapter 6 all at the same time. It's kind of a pain. All right, so here we know that this is 131. Here we know that this must be 104, right? The intercepted arc is double the inscribed angle. Well, it's 360. The only thing that's left is x, minus 104, minus 131. So if I subtract this, go ahead and just use a calculator, 360 minus 104 minus 131 is going to equal 125 degrees. So x is 125 degrees. So kind of a Swiss Army knife here of a lesson. Just sort of asks us to combine a bunch of stuff that we've done before and see what it comes up to.